Okay, so we are going to talk about heavy-tailed, continue on the heavy-tailed, but a subset of that is power-tailed. Now, the reason you need to know all of these three things that we're going to talk about in this chapter, power-tail, heavy-tail, self-similarity, long-range dependence, is because this invalidates much of the theory that was developed earlier. If you go and present a paper somewhere in the conference and you say, well, I'm assuming exponentially distributed this and that, immediately somebody will say to you, no, it is not exponentially distributed. We have and there are so many papers that show that this is heavy tail distribution. So what does heavy tail do? And what is heavy tail? So even if you don't want to use it, you need to know what it is so that you can answer the question at the time. Okay, all right. So it's heavy tail, but for simplification, whatever, this and that, we are using exponential. So heavy tail is very important because that is what the whole world has been shown to have these kinds of things, which I'm going to talk about today. And so power tail is a special case of heavy tail where the tail has a power function x upon alpha, which means when x goes to infinity, it goes down as inverse function of x raised to alpha. And alpha is called the tail index. And we saw an example, a simple example of a power tail is Pareto distribution, which actually has basically this, the CCDF is 1 upon x raised to alpha. And the PDF is basically you can distribute, you can differentiate the CDF, which is the cumulative distribution function, and get the PDF. Once you get the PDF, you can get the LF moment. LF moment is simply the expected value of x raised to L. So you could get the first moment, which is the mean, expected value of x raised to 1. You could get the expected value of x squared, x cubed, and so on and so forth. And if you do that, you will find out simply it is x raised to L times this function, and that integrates to this value. That integrates to infinity if L is greater than A. You can see here, x raised to L minus alpha. So if L is more than alpha, then when you put infinity there, in place of x, you get infinity. If L is less than alpha, then obviously you get a 0 when you put x equal to infinity because the power is negative. And when you put a 1, you get this value. So, so basically, there is only one special case when L is equal to alpha. When L is equal to alpha, this thing is basically A upon x, which has an integral log x, natural log x, and still it is infinity though. And so for all values of L greater than or equal to alpha, the moments are infinite. So if alpha is between 1 and 2, the variance and high order moments are all infinite. If alpha is less than 1, the variance does not exist, and even the mean is infinite. Okay, so Pareto distribution is helps us find if what is the whether means or the variance exist for the data that we have. So what is the effect of heavy tail? A random variable with heavy tail can have very large values with finite probabilities. Okay, and you will have many outliers. And sampling from such distribution results in mostly small values, but with few very large values. So you might be sampling, you'll get 1, 2, 1, 2, and suddenly you get 1,000. All right, and so when you get the mean, sampling statistics like mean or variance, those will be very small. Basically, your numbers will be very underestimate of what actually it is, because you will take all these little values and say, okay, the mean thing is this. A good example of, by the way, Pareto distribution or any of these heavy tail thing is we talked about the income or the wealth of the people. So 99% of the people have a small wealth. 1% has, large wealth. And so when you take the mean income comes out small, but really if you take a sample and take a mean. And so because most of the people will have 100,000 or less than 100,000 income, but there are people who have $1 billion income. right? So that's the kind of disparity you see in a heavy tail distribution. And so sample means are generally underestimates. And so when you do a simulation with that kind of input, if you have to do a simulation, you have the same problem, is that whatever you get has a very high variance, and therefore it takes a long time to complete the simulation. All right. And so here's one way you can calculate how long will it take. So it has been shown, and we are not going to show it here, is that if X has a tail, then X mean, X n bar, which is the mean, sample mean with n observations, and mu is the population mean, it is far from the, basically the difference between the two is of the order of C times n raised to 1 upon alpha minus 1. C times n raised to 1 upon alpha minus 1. This is the order of. Right? So if you want to get one digit accuracy, if you want to get k digit accuracy, then this value, the difference from the actual population mean should be of the order of 10 raised to minus k. You know, if it is order of 10 raised to minus 1, you get the first digit accuracy. K digit accuracy means that it is within the 10%. Okay, so basically k equal to 1 is 1/10. You should have 1/10, you know, let's say first decimal point should be correct. Okay, 2 digits means, you know, you will have 1% accuracy. And 3 digit accuracy is 0.1% accuracy, something like that. All right. So what I'm saying is right here clear is that the difference of the sample mean from the population mean divided by the population mean would be 10 raised to minus k. That's what you want. And if you keep solving it, you will find that the n has to be more than this value. 10 raised to log of c upon mu plus k upon 1 upon 1 minus alpha. Now the interesting thing is the alpha appears here. So if alpha is 1.1, alpha is 1.1, you can do all the calculation and you will figure out that to get this one digit accuracy, you will need 10 raised to 11 observations. 10 raised to 11 is a large number. This is only one part of the story. The second part of the story is that even the central limit theorem that we started with, remember what the central limit theorem said? That if you take large number of samples from any distribution, the sample mean is normally distributed. Things like that, right? That doesn't apply. That is only valid if the variance is finite. So the correct statement for sample limit theorem is that if you take a large number of observations from a distribution with finite variances. Finite variances means that if you write down, if you calculate the population variance or sample variance, it will be a some number, right? In these example, it will be infinity. So first of all, central limit theorem does not apply, and therefore the sample mean is not normally distributed. And if the sample mean is not normally distributed, then those confidence interval values that we use, the t values and z values and so on and so forth, they don't apply. So the whole statistics, now we have to rediscover the whole thing. All right. And that is why this is now of current interest to all the performance analysts, performance probability people and the statistics people. This is where most of the work is being done and being published, is what to do for heavy tailed and long range dependence and so on and so forth. All right. So here, I mean, and this is very sophisticated stuff, by the way, as I said, you know, is that it is, you know, I'm going to present a very simplified view of everything here so that you can understand. And it is important for you to know at least that part because that is what the real world is all about right now. All right. So heavy tail we understand and we understand the effect of it. And now let me show you some other effect here. So for example, if you had instead of MM1Q, you had MPTQ, where PT is the power tail. Instead of exponential, you had a Pareto distribution. If you had a power tail distribution, you will have Poisson arrivals because n, but you will have power tail service time. Then the Q length for large n will go to C times C is a function here of rho divided by n raised to alpha. Where C rho is a function of the traffic intensity rho, and if alpha is less than 1, the mean service time is infinite. If it is service time is power tail distribution, then obviously the mean is infinite if alpha is less than 1. And so the traffic intensity would be infinite, and the mean queue length will be infinite. So all your calculations about buffer overflow and all that will be off significantly. If alpha is less than 2, so it is more than 1, the mean might be finite, but the variance is infinite. And if the variance is infinite, then your confidence intervals, etc., would be infinite. And so that is the problem, right? Same thing applies to PT M1Q. If your arrivals have power tail distributions and the service is exponential, then you will get almost the same effect. The mean inter-arrival time would be infinite if alpha is less than 1. The variance would be infinite if alpha is less than 2. And so this is all, the problems. The only good news about heavy tail distribution is that it implies predictability. Predictability in the sense that if you know, say for example, memoryless distribution exponential has no predictability. You cannot predict what the next value would be given the current value. But with heavy tailed, if you know that the value is more than 10,000, then you know it will be, the probability of it being high is higher than probability of being lower. I mean, so the thing is higher the value, the time that since the thing has not happened, the longer it will take. So the probability goes up in that sense. So that's it. If heavy tail distribution has not run, task has run a long time, it is expected to run for an additional long time. Because the probability of x minus x, where x is greater than x. So we already have little x, we have already observed for that long, and we know that it has not finished. So now the probability of its being longer is higher than if it was before. So how do you check for heavy tail? Luckily, it is easy. Is that you just use a QQ plot and try to fit a Pareto distribution. QQ plot on a Pareto distribution. For a Pareto distribution, fx, capital Fx, is 1 minus x raised to minus alpha. And therefore, if you invert it, you get x is equal to 1 minus f raised to 1 upon alpha. So you don't need any table. You can just calculate the values for Pareto using simple Excel worksheet. Right? And so all you have to do is on a log-log graph, if you take log x and you plot it as 1 minus f, then you should get a straight line. Alpha equal to 1, alpha equal to 2 would be the slope of the line, basically. But the exponential will be here, which is basically much less than alpha. But this one is this one, right? Now, if you find that for your data, you have alpha equal to 1 or more, then you know it is a heavy tail. So this is the heavy tail part of it, and this is the not heavy tail part of it. Capital F is the CDF, cumulative distribution function, which is same as QI, quantile. So given a data, we can figure out whether it is 90th quantile, what is this 50th quantile, what it is. If you plot quantile, we are plotting CDF, right? So in a minute, I'm going to just replace this F with QI. So basically what we do is we plot log minus log, natural log 1 minus QI, where QI is the quantile value for whatever X values we have. And then we plot and then fit a straight line, then the slope of the line will be alpha. All right. So here are 50 observations. We write down them in a table, Xi's. We rank them from 1 through 50. And for each rank, basically if the rank is 1, means that this is the lowest value out of 50. And therefore it is 1 upon 50th quantile. Right? If it is the second value, it is 2 upon 50th quantile. It is the 50th value, it is the 50 upon 50th quantile. Right? So that is how we plot the capital F is the quantile. But instead of doing just 1 upon that, we just subtract 0.5 so that we get, because of the finiteness of this. So we get for 1, we will get 1 minus 0.5 divided by 50. And so on and so forth. The 50th would be 50 minus 0.5 divided by 50. So we get those quantiles. Then we get log x and log 1 minus qi. We plot that here, and we can get the sum of squares and sum of things like that to get just for linear regression. Whatever we do for linear regression, we get all those values, and we can get a straight line, and we just calculate the slope parameter. We don't need to worry about the offset. Offset could be non-zero, but we don't care for that. What we are looking for here is the slope. And there is no error, there is no regression. All we are doing here is we are trying to estimate, we're trying to estimate the slope of these dots. And one way to do that is actually just ask Excel, for example, to fit a trend line, and you can just read the trend line approximately whether it is more than 1 or less than 1, and you're done. So we are really not doing prediction or regression or anything here. We are just using the formula of the regression to fit a straight line so that we can find approximate slope. And another thing we have done is we are starting minus log so that this doesn't come out negative like it is supposed to be. See, for example, here if you go here, the log of 1 minus f is negative. So we plot minus so that it comes out on the positive side. So one of them is measured, one of them is theoretical, quantile, right? And I had tough time figuring out where is what. But for this combination of axes, it does give you a slope of 2. If you change the axis, you get a slope of half. And I generated this data with a slope of 2. So this is the right axis, I know. This is how you're supposed to plot. You're supposed to plot xi on the x-axis and minus log 1 minus qi at the y-axis. If you do this, then the slope will come out exactly what you generate. And I generated lots of different sequences to try it out. QI, basically alpha of 2, 3, 4, 5, 6. If it is the other way around, it just goes the other direction and gives the wrong answer. We want alpha to be less than 1 if you want to be short range dependence, right? So if you try to fit a Pareto distribution, you want alpha to be less than 1 for short range. For more than 1, it says long range. Now, right? And long range is kind of difficult. Sorry, not short range, long range. Heavy tail means heavy tail. So, no, not heavy tail. Alpha more than 1 is heavy tail. Let's go back to this. This is heavy tail. One more thing is that 50 observations are too little to do anything for a heavy tail distribution. Right? I mean, you really need 5,000 observations here. However, I don't have paper space to put 5,000, so I'm just going to do the example with 50. See what I mean? If you really want to prove something is heavy tail, you don't take a small sample. You take a big sample. By definition, you require a big sample because heavy tail means, sample size required is large. All right, that finishes heavy tail. Now then there is a second concept which is very popular nowadays is self-similarity. Self-similarity is also known as fractal. And fractal actually came from geometry because most of the things in the natural world are fractal. You have heard the word fractal before. I've seen some of these pictures before. Basically, fractal means that if you take a microscope, anything with zooms this thing, you will find exactly the same thing as the big object. Keep going in, you will find the same thing. In this triangle, we take this triangle and look at under microscope, you will find triangle inside a triangle inside a triangle inside a triangle. Same thing again and again. And in fact, one of the good exercise for you would be to be able to draw this thing. And actually, is that you write a routine to draw a triangle of this size with X here, and then just call that routine to draw 4 triangles and 4 triangles and 4 triangles, and you will get a nice picture. You can do this with the squares, you can do with pentagon, and you can do with anything else, okay? So you will get nice fractal pictures. So that is for your pastime. But anyway, even the leaves are fractal. If you see a leaf under a microscope, you will see that it consists of. If you take a tree, you will see that all the branches, the branches and the branches and the branches, these are all the same shape. All right, so the world is fractal. And that means you cannot use the normal geometry because normal geometry assumes that the perimeter is finite. of objects, right? But the parameters of the natural objects is infinite. All right. This is the same situation in statistics. We think the variance is finite, and we develop the whole theory. But now we find out that the variance is infinite, and therefore the processes are self-similar. And so we are developing a new theory. All right. So what is self-similarity of stochastic processes? Basically, if you take a process xt and you scale it in time, so instead of xt, you look at xat, where a is your scaling factor. So let's say your scaling factor is 2, then you are looking at twice the magnitude. You're taking a microscope and looking at more detail inside. If it turns out that xat follows statistically a formula that would have been for x a raised to h xt. All right, this is if it followed a distribution for this, then it is self-similar. Obviously, this means that the distribution of x for different times is different, right? When we assume the stationarity, we said the distribution is same for all times, right? Here, if you find that you have a process that does not have the same distribution for all time, but if you look at xat, the distribution is a raised to h xt. So basically, whenever you scale time, you see the scaling in magnitude. If you do that, then that is a self-similar process. Okay? And as a result of this relationship, the mean would be a raised to h time. Mean of x raised to at would be a raised to h time mean of xt. The variance of xat would be a raised to 2h times variance of xt. And the third moment would be a raised to 3h times the third moment. And the fourth moment would be a raised to 4h times, and so on and so forth. And if you find that this kind of relationship applies for all moments, then it is called strictly self-similar. If it only applies to the first two moments, then it is called self-similar of the second order, or the first order will be just simply for the mean. All right. So the order up to which this relationship of scaling in time is equal to scaling in magnitude applies is the order of this self-similarity. So how do you get a self-similar process? Let's say you have white noise, ET, where ET is simply normal 0, 1. Then you construct another process where you multiply ET with T raised to H. So you take E1, E2, E3, E4, E5, E50, and then you multiply it by 1 raised to H, 2 raised to H, 3 raised to H, 4 raised to H. So now you have a different series which is not stationary anymore. Right? If mean actually it changes with time, actually it is going up with time. So this series is self-similar. Why is it self-similar? Because you can see when you want to get xat is at raised to h times z, which is a raised to h times xt. So this will have the mean, which is a raised to h times the mean of xt, which is 0. It will have variance, which is a raised to 2h times the mean of. This is an example, right? And by the way, this h, capital H, always written as capital H, is a Hurst exponent. Why is it Hurst exponent? Because this is this scientist who first found out this. And so he used the letter H for this parameter, and we all use that letter H, and it's called Hurst exponent. And if it is, okay, so that's all about self-similar. Now we go into actually dependence. Yeah? I'm sorry, what is it? What is what? No, actually, I need to get into, the thing here is what is happening in the real world is that a lot of people confuse self-similarity with long-range dependence, almost 100% of the people. And therefore, I have to just introduce the self-similarity now and then go into long-range dependence and show the difference. Before I go to long-range dependence, I want to show you short-range dependence. If you have an autocorrelation function which goes down to 0 fast, we say it is a short range dependence because the dependence does not live for very long. Right? Autocorrelation function indicates the dependence. So how do you say that it's going down very fast? The definition of fast is that the sum is infinite. If you take all the autocorrelation function, autocorrelation at lag 1, lag 2, lag 3, lag 4, lag 5, lag 200, or lag up to infinity, you add up. If the sum is still finite, then this is a short range dependence. All right. An example of short range dependence is AR1. What is AR1? And autoregressive of the order 1. Right? So that is XT is equal to, and I'm assuming 0 means, so I'm just ignoring A0 here for the time being. So A1 XT minus 1 plus ET. That is AR1. Right? For this process, you can show that the autocorrelation function is simply A raised to K. It goes down exponentially. And if you add up to infinity, you get 1 upon 1 minus A1. It's finite. And so that is short range dependence.